In this video, we're going to solve systems of equations using matrices. Sorry for the typo at the top there. Using matrices, which is a plural for the word matrix. We'll be able to set up a matrix in our calculator to potentially solve systems of equations. And the only new vocabulary for this video is that we're going to be using the word array, matrix, and you may hear me say row operations again. In the last video, I had mentioned that you can search the term row operations for a further explanation, but again, you may hear me say that in this video too. So first off, we'll say this, that an array of numbers is formed by arranging them into rows and columns. So if I took a bunch of numbers and I arranged them into rows and columns, that would be what we call an array of numbers. And when it comes to solving systems of equations with an array, each row and column must be full and no element can be empty. So if we're going to end up with something that has 3 columns, like this example here, and 2 rows, we can't just leave one of these empty. Now, in place of being empty, we could write the number 0, and that would be totally fine. But the number 0 is indeed a number. It's not leaving this position blank. So we cannot leave any position blank. Nothing can be empty. And we'll describe these matrices by the number of rows and columns that they contain. So for example, most of our system of linear equations from this unit can be represented by what we call a 2 by 3 matrix. It has 2 rows and 3 columns. This example here, this matrix A, has 2 rows, 3 columns. We call it a 2 by 3 matrix, and we sometimes even write it this way. Letter A with subscripts 2 cross 3. It's not really a multiplication sign, although it looks like the multiplication X. We would say 2 by 3. This is a 2 by 3 matrix. So when we have our linear equations and they're written in standard form, if you recall, standard form would look something like this. Some number a times x plus another number b times y equals some third number c. This is what we call our standard form. If both of them are written in standard form, then our coefficients from each row or each equation will act as the row elements in the corresponding matrix. And the columns are effectively the row elements, or I'm sorry, the columns are the coefficients as well, but you'll notice that the columns are organized by what they contain, either the x coordinates, the y coordinates, or the solutions, or the values that are on the equals, on the right side of the equal sign. We can use this picture on the left as an example, and it's super important to remember that each row and column must be full, and each equation must be written in standard form. And to be honest, it's a whole lot easier when we go in alphabetical order. So standard form does imply that, but it's really important to notice that too, that the x variable will be listed first, the y variable will be second, and we'll put any equal sign with any plain old numbers on the right hand side. We need the equals and the numbers on the right hand side to make this process work. So here we have a system of equations. Sometimes we put this brace out front, and we can see that x plus 3y will equal 7, and simultaneously 3x plus y will equal negative 8. If there is a solution to this system of equations, then a matrix can be used to solve it, and we'll set up the matrix this way. We have the matrix brackets to begin with, and then the coefficients. We didn't have a number written here in front of the x, but we can assume that it's a 1. That's why we have a 1 here. Then a 3y, so we'll just write the number 3. We just want the coefficients. And then finally 7 at the end. We have 7 at the end. Then 3x, 1y, and negative 8. And that's where our matrix comes from. And when we type these into the calculator and let the calculator do the math for us, we will almost never include this vertical bar. I know the textbook that I'm borrowing this from says to draw a vertical bar to replace the equal sign, and I suppose that's good habit if you're going to do the row operations yourself by hand, but we're going to let the calculator do the work for us in each of these examples. So you will not see that bar when we enter it into the calculator. So here we go with example 1. In this example and example number 2, I don't want to solve this yet. I just want to make sure that we can set these up on our own. So I'm going to do this first one, and I'm going to leave the second one up to you for a challenge. And then you can check your work after you've tried it. But here we have a set of linear equations. We have 2 of them, and the linear equations do appear to be in standard form. We have x and then y and then a number, x and then y and then a number. So if this is already in standard form, we can now just borrow the coefficients and use them to build our matrix. So to build this matrix, I'm going to start with the top row, and I'm going to call that 2, 1, and then 9 for 2, a coefficient of 1, and a coefficient of 9. Then in the second row, I'm going to call this one a 1. We have 1x. I'll have to call this one a negative 6, and this one, of course, a negative 1. And that appears to be a good 2 by 3 matrix that represents this particular problem. And I'll use the square brackets to group it. And I think that would be a fine answer for this example. This is the setup. Now take a look at example number 2. Admittedly, it's going to be a little bit more challenging because we now have 3 variables, x, y, and z. But utilize what you know from the first few minutes of this video and see if you can establish the matrix that could be used to solve this system of equations. Please pause the video now and resume playback in a moment to check your work. Now you may or may not be able to complete this on your own in its entirety, but I do want to jump in right now and offer you a bit of a hint. This top row was okay. We already have our equation in standard form. We have x, then y, then z, and the number on the right-hand side. In the second row, however, we almost have it, but there's something that's missing. There was no y value. So remember what I said about each row having to be full. I wouldn't be able just to use an x and a z coefficient. I need a y coefficient as well. So you'll notice that I'm going to transform this equation to x plus 0y plus 3z equals 12. And then finally, in the third row, this one's even trickier still. We would like this in standard form, so that means all x, y, and z coefficients and variables on the left side, while any other plain numbers should be left on the right. So that means I've got to move this negative 5x to the left side, and I do that by adding 5x to both sides of the equation. That leaves me with a positive 5x, a positive y. There are still no z values, so 0z, and that would equal a positive 1 on the right. So now with these 3 little hints, can you set up the matrix to be solved this time? Go ahead and pause the video again and try to finish this out if you haven't done so already. And here we go. With the coefficients in place and everything written in standard form, I think we've got a pretty good result in this format here. 1, negative 3, 1, 6 across the top, 1, 0, 3, 12 across the middle, 5, 1, 0. Yeah, this is a positive 1. So I almost confused myself there. Positive 1 in that bottom right-hand corner. That looks pretty good to me. Well, now that we've successfully set up the matrices, let's see how we would go ahead and solve them. So again, if we have a matrix that represents a system of linear equations, we can use that matrix to solve the system of equations. Now, many computers and even handheld calculators can perform the row operations necessary to isolate and solve for unknown variables. So the row operations that are going on, there's a lot of work that would be used to, or be completed to isolate a variable, and the calculator can make quick work of that. Computers can make quick work of that too. So we don't need to observe or note each of the row operations. We just are interested in the final answer, if there is a nice answer for each of these systems. For this class, I'd say it's most important to remember the following keystrokes to allow the calculator to complete this task. We're going to press the menu key on our calculator, then press the number 7, then the number 5, then menu again, then 7, then 1, and the number 1. So if you can memorize this pattern, menu 7, 5, menu 7, 1, 1, that's the process necessary to set up your calculator to solve a system of equations using matrices. So here we go. The matrix for this example, number 3, is going to look something like this. 9, negative 2, 5, 3, 7, 17. This was already set up for us in standard form, and we were ready to go. So when I go to the calculator and press menu 7, 5, menu 7, 1, 1, we'll go ahead and set up a 2 by 3 matrix and allow the machine to do the work and solve for us. Okay, so as I had mentioned several times in class, I'd like for you to turn on the calculators, press the home button until you get to this screen, and we'll choose to create a new document. We won't save the last user's work if we're prompted to do so. We do want a regular calculator page, so we'll turn that on, and the menu shortcut, or I'm sorry, the keyboard shortcut to get where we need to go is menu 7, 5, menu 7, 1, 1. Let me try that again. Menu 7, 5, menu 7, 1, 1. So that's the keystroke that will allow us to create a matrix. And this little command back here on the screen, this is what's going to do the row operations for us. I'm not going to get into the specifics with that now. Now in the example number 3 that we're working on, this is a 2-row, 3-column matrix. So we need to specify that. 2 rows and 3 columns. This is a 2 by 3 matrix. We'll press OK. Now you can see the calculator has given us space to work. So I'm going to type in the numbers here. 9, negative 2. These are all the coefficients from the matrix. 5. And I'm just pressing the tab button to go in between each of these blocks. 3, 7, and 17. Now it's important to note that the first column was an X column, the second column was a Y column, and the third column was a set of results. So when I press enter here and I get my resulting matrix, we can read it to interpret whether a solution has been found. Now according to this matrix, we're saying that 1x plus 0y equals 1. So essentially this row is now telling me that x must be equal to 1. We have 0 x's in this column, plus 1y must be equal to the number 2, must have a result of 2. So again, if 0x plus 1y equals 2, then y by itself must be 2. So this matrix has turned into this one. And this matrix implies that x is equal to 1 and y is equal to 2. Or in other words, our solution is 1, 2. No algebra, no graphing, no tables necessary. The matrix method was able to solve this for us with very little effort. And we can do the same with this example here, and you'll notice we're back to a 3-variable system, and this time we changed it up once again. We have A, B, and C acting as our variables. Take note that in the center of the third row we are missing a B value, so we can't have an empty space in our matrix, so I'm going to replace that with the number 0. So the matrix that we're going to bring to our calculator is going to look something like this. 2, 3, negative 1, 1, negative 4, 9, 2, 8, negative 2, 0 as our placeholder for no B values, 2, and 3. We're going to apply the keyboard shortcut to this matrix. Notice that this is a 3-row, 4-column matrix, so we better enter this as a 3 by 4, and we'll let the calculator compute the results for us. So once again, the keyboard shortcut is menu 7, that brings us to the matrix menu, 5. This is the command that we would apply to do the row operations for us. Then again, menu 7 for the matrices, 1, 1. We're going to create an empty matrix. So we need 3 rows. I'll tab down and type 4 columns. We'll press OK. And now we've got a 3-row, 4-column empty matrix ready to be filled. We have 2, 3, -1, 1, then -4, 9, 2, 8, and then finally -2, 0, +2, and 3. So I think we've got everything entered exactly as we had written it on paper. This looks like the set of coefficients for the problem that we're dealing with. So when I tap enter here, this matrix should represent our solution set. Well, let me copy it down and then we'll talk again about what's being stated here. So we had 1, 0, 0, 0, 1, 0, 0, 0, 1. That's the pattern on the left side of the matrix. And on the right we had a 1/2, a 2/3, and a 2 as the result. So here again, when we set this up, this was our A column, our B column, and our C column. And we're effectively saying that 1A plus 0B plus 0C has got to be equal to 1/2, because this last column over here represented our solutions. Well, if 1A plus 0B plus 0C is equal to 1/2, these don't even matter in that equation, and we're stating that effectively 1A is equal to 1/2. So we can say that A is equal to 1/2. This middle row operates the same way. No A's, no C's, but 1B must be equal to 2/3, so we can state that B is equal to 2/3. And then finally, C must be equal to 2. So as long as our matrix gets reduced with the row operations into this pattern or this format, with 1s down the diagonal and 0s everywhere else, as long as we see that pattern, then I believe we have an acceptable and independent solution to this system. Now to finish this out, we have 3 answers, A, B, and C, and even though they're not X and Y or X, Y, and Z, we can still report them in an coordinate form, or what we would call in this case an ordered triple instead of an ordered pair. So the triple A, B, and C could be reported this way, or we can simply state them as 3 individual expressions. So I think that's a good place to stop with this example. Again, this is a bit of an extension for what we're doing in class, but I thought you might be interested in seeing it. And if you'd like to use this technique on a quiz, as long as calculators are permitted, I have no problem with that, as long as you explain your process and show your work. Thanks for watching.